Okay, hello everyone, and today we are going to talk a little bit more about the expanded octet or violating the octet rule in the periodic table. So as you see from the previous examples we solved in the previous lecture, like for nitrogen monoxide and some other molecules, they actually violate the octet rule, and therefore there is nothing to do about that. And these elements, some of the elements, they violate the octet rule by having less than 8 electrons, and these elements, for example, they're like beryllium Be, which is in the second group, and boron and aluminum. Usually carbon, nitrogen, and oxygen and fluorine, they cannot break the octet rule except in a few cases. But as you will see today, many of the elements in the periods third and fourth and so on, the lower periods, they can have an expanded octet, which means they can have more than 8 electrons, just like the case of aluminum iodide, as you will see here in this example. So for aluminum iodide, you can apply this also to aluminum chloride, so Al(I3). So if you want to do the lowest structure for this, aluminum is in the third group and therefore it has 3 electrons, and iodine is in the seventh group and this is 7 times 3, and you get here 24 electrons. If you do the lowest structure for this, of course you have to do it in 90-degree angles, and you need to distribute the electrons, the rest of the electrons, 24 electrons. You can do that, satisfy the octet rule for iodine at least. And you see here 8 times 3 is 24, so there is nothing left for aluminum. There are no lone pairs here in the aluminum. This is the lowest structure for aluminum iodide, and it's a correct lowest structure. And you see here that aluminum actually in the middle has only 6 electrons. Okay, so this compound, this molecule actually violates the octet rule. So violates the octet rule, but it's the correct lowest structure because it does not have enough electrons to satisfy the octet rule, and therefore we have to accept this fact. So this is a shortage of the octet rule. On the other hand, we have elements that they can exceed the octet rule, just like this element PF5. If you see here, this is the lowest structure for phosphorus pentafluoride. All the fluorines, they have 8 electrons around them, while phosphorus in the middle, if you count the electrons, it's going to be 10. So 2, 4, 6, 8, and 10 electrons, and therefore PF5, it has something we call expanded octet rule. That means it has more than 8 electrons on it. And there are also a few examples in the book. Even some noble gases like xenon, for example, people think that rare gases or noble gases, they don't make compounds, but actually xenon, as you see in this example, xenon can make compounds actually, and xenon tetrafluoride is a very famous example where the xenon it's attached to 4 fluorine atoms, and if you count the electrons around xenon, you will have them to be 2, 4, 6, 8, 10, and 12. Actually, there are 12 electrons around xenons. So anyway, we are going to use these examples anyhow again in the next chapter. So I'm gonna stop here for this chapter, and I wish that you can do the questions and the homework on time. But let's move on to chapter 10, and we're gonna talk more about this expanded octet rule when we go there. Okay, so in chapter 10, of which is the last chapter in this course, we will speak about molecular geometry, which is the 3-dimensional arrangement of atoms in a molecule, and this is actually the real arrangement or the real geometry of the compound. And from the geometry, we can know more about the density, we can know more about the melting point of the molecule, the boiling point, and the reactivity, and so on. So we can infer so much information, physical and chemical information, from the molecular geometry. Now, so there are three actual theories to determine the geometry of molecules. One of them is the Lewis structure, which is the weakest, and it's the one that it does not actually give you the actual geometry of the molecule. There is one called the VSEPR, valence shell electron pair repulsion, and we're going to study this today. And the third one is the molecular orbital theory, MO theory, which unfortunately we have no time to cover that. But the MO theory is actually the best one because it will give you the exact. It will give you the correct geometric information about the molecule. Now for the VSEPR, I call it VSEPR, the valence shell electron pair repulsion. From its name, you have valence shell, so we're talking about the valence electrons, and you have repulsion. Okay, so that means these pair of electrons will cause some repulsion between them, and it will push the molecule to have a shape that is actually in three dimensions that will reflect the actual shape of the molecule, as I'm going to show you in the next examples. Now, let's take an example, and I will show you what the VSEPR are all about. Let's imagine that we are going to talk about methane, which is CH4. Now CH4 has carbons in the fourth group, so we have 4 electrons, and plus 4 times 1, so we have 8 electrons total in this molecule. So we start by writing the Lewis structure, or drawing the Lewis structure. So carbon in the middle, we have 4 H's, and Lewis does not have any angles except 90 and 180. So this is actually the Lewis structure of methane. The angle here, according to Lewis, is 90 degrees. But everybody knows that this is not actually the exact structure of methane, because the angle in methane is not 90 degrees, in fact. And Lewis only thinks in 2 dimensionals. But if you think in 3 dimensions, you will see that you have a lot of empty space in front of this molecule. And there's also empty space in the back of this molecule. So the hydrogens are here drawn in paper in 2 dimensionals. But if you think in 3 dimensionals, the shape of methane should be, we can do better job than this. So again, if you go to fit.com, and this is a good tool to study VSEPR structures from now on, and you go to chemistry, there is one that is about molecules structures, shapes of molecules, it's called. Okay, so molecular shapes, click on that. So if you can click on rare molecules and choose methane, methane should be here, I think this is the one. Now, this is the actual structure of methane. This one is drawn in 3 dimensionals. It has carbon in the middle. There are 4 hydrogens, but the 4 hydrogens are arranged in space in a way to minimize the repulsion between the electrons, because these bonds between the carbon and the hydrogen are formed of electrons, and these electrons are actually they repel themselves, and they cause the 4 hydrogens to be arranged in space like this. This shape is called tetrahedral. Tetrahedral. This is a very famous shape for molecules. Okay. Now, the angle here between the HCH is around 109 degrees. It's not actually 90 degrees. It's 109 degrees. Okay. So this is one of the shapes that. And if you want to draw this in paper, it's difficult to draw these things in paper. But if you want to draw it in paper, you can imagine that you have a carbon here in the middle. You have an edge that is going up, make an edge, another edge with maybe an open angle a little bit. You can put an edge here, an edge there. This angle is 109 degrees. Okay, so usually in the book, or yeah, this is how you draw methane. It's a tetrahedral structure. Okay, so that's the first example in our story today. Next example. So this next example probably is let's take another example, which is boron trihydride, or even we can take the aluminum, the Al(I3), which is actually also equivalent to AlCl3 and BH3. These are all the same. They have the same geometry. So now BH3, it has 3 electrons and H hydrogen. So starting with Lewis will give you a 90-degree angle of that. That's Lewis. If you want if I ask you to draw the Lewis, you draw it like that. It's 90 degrees. Okay, but this is not the VSEPR structure. This is not the actual structure. The VSEPR structure, there is no way to think why there is so much space here. Why this is 80 degrees? That's what VSEPR. If you want to think about the VSEPR, you ask yourself why there is so empty space here. VSEPR says that there is repulsion between these two pairs. Okay, this is a pair of electrons, and this is a pair of electrons. So there will be repulsion between them, as well as here. Okay, and that will push these bonds at the end, and that will lead you to be maybe this hydrogen will stay as is, but these hydrogens will repel themselves a little bit, and you will have equal 120 degrees angle. Now, what is the difference between the two? This is the Lewis structure in the beginning, and this is a VSEPR structure. This is called molecular geometry. Molecular geometry. So the molecular geometry here, we call this a trigonal planar. Just like the fan in the ceiling, if you look at its shape, it's called trigonal planar. So we have seen now so far two examples of molecular geometries. One is called tetrahedral, and this is the other one, trigonal planar. If you go back to fit.com, and you can choose an example of BF3 or CL2. No, that's not the one. This is difficult. Okay, so it's not. We can go back. Okay, we can go back. I think models instead of real molecules. Okay, so you can play with the model now. This is you put two bonds here. I want to make another bond, so I'm gonna use my mouse and add another. So okay, this is the one. This is trigonal planar. Trigonal planar. You see how beautiful it is? It's a very beautiful molecule. 120 degrees angle between each atoms. Okay, it's planar, so it is written in 2D. And this is an example of BF3 or AlCl3 and so on. So this is the idea of the VSEPR structure. Now, the VSEPR has actually okay, so okay, the VSEPR has actually 5 families or 5 groups. Okay, the first one. Okay, let's take another example before we go into this table. The other example I want to give you is a linear one. So we've talked about methane, and then we talked about this one. Let's take another example, which is BE, for example, Cl2. Okay. Now beryllium is in the second group, so it has only 2 electrons. And let's just simplify that to BeH2, just to make it easy. Okay. So BeH2. So this one has 2 electrons only because it's a group 2 and plus 2 times 1. And this one, as I said last time, this has only 4 electrons. So if you want to draw it, it's BeHH. Okay, this is the lowest structure. Okay, oh sorry, there are no electrons here. This one violates the octet rule. This is the lowest, and this is where maybe Lewis agrees with VSEPR structures, because this is actually the same as VSEPR. There is no the pair of electrons here are repelled in a very good way. They are away from each other, okay, and there's 180 degrees angle here, and therefore this is actually the same as VSEPR. So VSEPR as well, VSPR, you can draw BeHH. The only difference between the VSEPR and the Lewis is that you don't draw actually the electrons if there are any. So here in the okay, anyway. So this is called linear structure, linear, because it's just like a line. So there are 5 molecular geometries there are actually 5 molecular geometries in the VSEPR. There is the linear, trigonal, planar, tetrahedral, but there are also other 2 that we are not required you to study in this course. But for now we have the linear and the trigonal, planar, and the tetrahedral. Linear has two electron pairs, either bonded or non-bonded. There is the trigonal planar has a 3, and the tetrahedral has 4. There's also another 2. They have 4 and they have 5 and 6 electron geometries. The angle in the linear is 180. Trigonal has 120, and tetrahedral has 109.15 degrees. Now, we have 2 things in the VSEPR structures. I will tell you that when I give you this example about water. Now, let's draw a VSEPR, valence shell E electron pair repulsion, for water. The way you do that, the first thing you draw the first step of drawing a VSEPR is you have to draw the lowest first, okay? And the second step is you think about the repulsion of electron pairs, and then you go to VSEPR. So the first step of drawing any VSEPR structure is you must do the lowest, and that's why lowest is important. Although it's wrong, but you have to do it, okay? So the way you do that, of course, you count the electrons first for lowest. So you have oxygen that's in group 6, so it has 6 electrons plus 2 times 1. So that's 8. So you must have 8 electrons in your structure. So you put oxygen in the middle, H here, H there, and clearly here you have only, how many? You have 4 electrons. There is also 4 left. So you put them in oxygen. Okay. So this is a water molecule, which is Lewis. And everybody knows this is not the actual structure of water. Why? Because these 2 pairs of electrons, they repel themselves. Okay, they have to sit in space in a better way. And therefore, we go from this one to the known structure of water, which is oxygen, 1 electron here, 1 electron here, HH. Now, why this is happening? This is happening because here you have 4 electron pairs, okay, that repel themselves. You have 1, 2, 3, and 4. In VSEPR, we don't differentiate much between the lone pairs and the bonding pairs. They're all electron pairs and they all repel themselves. Because of the fact you have 4 groups of electron pairs, this will lead you to a kind of a tetrahedral, actually. This is a tetrahedral structure. Now, if you're talking about the arrangement of electron pairs, this is called tetrahedral, because you have 4 electron pairs, okay? But the shape or the molecular geometry of this, of water, will be called bent structure. Bent means the structure of water. You have just like that, number 8 in Arabic. So water actually belongs to the tetrahedral group, but it is in the but it's in a bin shape. In fit.com, you can simplify this by saying, okay, let's start from the beginning. You start with one bond. This is for, let's say, for oxygen hydrogen. You can click here, linear. When you add another bond for the hydrogen, you see this is still linear. You can talk about this is like the BeH2 example, but I need to add a lone pair to the oxygen in the middle. So you click on one lone pair and another one. You have two lone pairs. Now watch this. This is the water molecule. You have oxygen and you have two lone pairs of the oxygen. Okay, they of course the lone pairs when we draw electrons, as I said many times, electrons are not actually small circles or small dots in that piece of paper. They are existing in an orbital, and the orbital has space. Okay, it occupies big space, and therefore these lone pairs, they actually need some space, and actually they need more space than the modern electrons. Lone pairs, they need more space than electrons. And if you read here, it says the electron geometry or the arrangement of electron pairs, it's tetrahedral, but the molecular geometry is bent, or it's called the molecular geometry or the molecular shape. Okay? So we have two things that we need to talk about in this chapter. We have something called the arrangement of electron pairs, which is the name of the big group or the big family. Okay, imagine you have a family. So we have three families so far. We have the linear family in terms of, let's look at this table. Sorry, it's called the arrangement of electron pairs, and this family. There are five families, so we are only studying three here. We have linear, trigonal, planar, and tetrahedral, and each family has some kids or has some children or shapes. The linear has only one kid or one shape, which is linear. Trigonal planar actually has two shapes, and tetrahedral has trigonal planar has two shapes, and tetrahedral has three shapes. So we are going to study. So for okay, here we go. So this is the most important table in this chapter, in slide 17, and this is the table that you must pay attention to. So as I said, we have three families, three arrangement of electron pairs. For the linear, there is only one shape, which is the linear. For the tetrahedral, we have three. The tetrahedral, the arrangement of electron pairs, it could be tetrahedral, and the shape is tetrahedral. Okay, or we call it molecular geometry. And there is also trigonal planar, and there is also bent. And then the water is one example of the very last table, very last row here in the table, where you have tetrahedral arrangement of electron pairs and you have a bent geometry. Okay, and the angle is 109.5. Let's move on to another example so you can grasp this better actually. Okay. Now, let's think about ammonia. So ammonia is also a nice example. Ammonia is an H3. If you want to draw the VSEPR or the actual structure of ammonia, you start with Lewis. So Lewis, nitrogen is a group 5. So with the hydrogens, you will have 8 electrons in total. And you start with Lewis. So this is Lewis, Lewis does not believe in any angles except 90 degrees. So in Lewis, the angle is 90 degrees, which is the wrong structure. I mean, it's the correct Lewis structure, but this is Lewis structure. Okay, in terms of Lewis, it's good. Everybody is satisfied with the rule and everything, but this is not the VSEPR structure. If you want to go to VSEPR, you want to think as in terms of electron repulsions. Why? Again, there is so much empty space here. There is so much empty space, and there is, by the way, there is one lone pair here. Okay, so what happens is that these electrons, again, they repel themselves. Now you want to think about what is the number of electron pairs in this. Okay, you have 1 bond, 2 bonds, 3 bonds, and the lone pair. So you count the bonding and non-bonding, you count them all together, and you have 4 arrangement of electron pairs. So because it's 4, that means it's tetrahedral. So that means the arrangement of electron pairs, it's tetrahedral. So ammonia actually belongs to the tetrahedral group. But tetrahedral, as we said, it has 3 shapes. We have a shape that is called tetrahedral, which is like the methane. We learned also that tetrahedral has bent structure, just like water. And now we have another shape for ammonia, and we need to know the name of it. Now, what is this called? Let's go to fit.com and discover what is ammonia called. Let's start from the beginning. You can click here on the right bottom side. You have a restart. This is a nice tool in fit.com. It will teach you a lot. Now let's try to draw ammonia here and see what fit will call it. Okay. Fit uses molecular geometry for arrangement of electron pairs, and it's a bit confusing here. But anyway, now let's try to put some. So ammonia has 3 hydrogens. So let's put another hydrogen here. Okay, so that's it. So this is the like BH3. But the difference between ammonia and BH3 is that ammonia has a lone pair on the middle. So let's add 1 lone pair. Oh, nice. Okay, look at this. Now, the electron geometry, or what we call in our book, the arrangement of electron pairs, is tetrahedral. And this is called trigonal pyramidal. Trigonal pyramidal, you see? It's beautiful. Why it's trigonal? Because it looks like a pyramid. You have a pyramid between the 3 hydrogens and the nitrogens, and this pyramid is its face is a triangle. It's not like the pyramids in Giza, Egypt. This is not the Egyptian pyramid. This is a pyramid of triangles. You have a triangle here, triangle there, and triangle in the bottom. Okay, with a lone pair sitting in the top. This is called a trigonal pyramidal, but it also belongs to the tetrahedral family. So here, this is called in the question mark. This is called trigonal pyramidal. Remember, this is not trigonal planar. This is trigonal pyramidal. Okay. If you remove the electron pairs, this is now another family and another children. This is a totally different story. The arrangement of electron pairs is a 3, so it's called trigonal planar, and the shape is trigonal planar. Okay. So to summarize this, to summarize the VSEPR theory, I'm going to make a table here that summarizes everything. So the book is using, okay, so for methane, for example, CH4, which looks like this. He is using the convention of AB4, where you have A is the central atom and B is the bonding atom or bonding electron, okay? So in the case of water, you have, because the VSEPR structure looks like this, you have A, which is a central atom. You have 2 bonds or 2 bonding pairs. You have also 2 lone pairs. So sorry, AB2, A2. That's so in total you have 4 as well. And for ammonia, it's gonna be actually, you have central atom, you have 3 bonding pairs, and you have 1 non-bonding. So again, there are 4. Okay, so this is just a convention that the book is using, so we can use that as well before we go into the table. Just asking you what is the AB, AB4, AB3, and these things. So number of electron pairs doesn't matter if they are bonding or non-bonding. So you have 2, 3, and 4. Okay. So this is called arrangement of electron pairs. Sometimes they call them electronic geometry, okay? Some books, they call them electronic geometry. We have the linear, and we have the trigonal planar, okay, so this is linear, this is a trigonal planar, and this is tetrahedral, okay? Now in the linear, we have something called molecular geometry, or simply we can call it the shape. Okay? In the linear, there is only one shape which is linear. An example is BeAH2, for example. Okay, or Be or CO2 actually is linear, and so on. You'll have so many examples, but this is very famous examples. Okay. For the trigonal planar now, you have two shapes. There is one that is called trigonal planar. So each family has children where, just like the Arabic families, the big one, the youngest child is named after the father. It's trigonal planar. But this one has also bent structure, which we didn't see yet, but we're going to see it soon, okay? The trigonal, this is an example of, so trigonal planar, we saw this ALCL3, but this one, the bent, maybe SO2, or I forget, there is an example I will show you the example later on. For the tetrahedral, it has three children, or three molecular geometries, okay? One is tetrahedral, one is trigonal pyramidal, and one is the bent, like water, and this is like ammonia, and this is like CH4. Okay, so see here we have a bent that belongs to tetrahedral, so trigonal planar, and we have a bent that belongs to the tetrahedral. You have a child or a shape that is belong to trigonal planar. We have a bent structure that belongs to tetrahedral. So it depends on the number of electron pairs you can do that. Okay. There's a better book, of course, there's a better table in the book, of course. It's more nice and more arranged, but this is just the idea. There are also two other groups here. There's something called octahedral and trigonal pyramidal, which are not required. And these groups, of course, they have more children or more shapes, as we're going to say. So these are all here. You have here, what is it? You have trigonal planar with its children. You have tetrahedral and tetrahedral as well, and so on. Okay. Let's solve some examples on the VSEPR and try to figure out the shapes and everything. Do you have anybody has any questions so far about this? Before I do examples, anything yet you don't understand? Okay. So use the VSEPR model to predict the geometry of the following molecules and ionic ions. So ASH3 is the first one. And we have OF2, AlClO4 minus, A3 minus, C2H4, okay? Let's start with OF2 because it's the easiest one. And then we go back, no worries, we'll do with the ASH3. ASH3, so if you go to the periodic table, AS is right here, it's under phosphorus, so it's a group 5. So we'll do this is drawing Lewis and Whisper. It's actually fun. It's something really lovely. I enjoyed doing this because teaches a lot of things. It's in group 5, so we have 5 electrons plus 3 times 1 for the hydrogen, so we have 8 electrons in total. Okay, and that means you want to put a central atom in the bottom and make at least single bond with each hydrogen. Hydrogen cannot make double bonds. So these 6 electrons, we have 2 left, so we put them in acetylene. This is called the Lewis structure for this guy. Okay, how about VSEPR? Can we think about VSEPR? In order to do VSEPR, you have to count the number of electrons around the central atom. So you say number or arrangement, number of electrons, number of electron pairs is equal 4. Why 4? Because you have 1 electron pair, you have 2, you have 3, and you have 4. So this actually belongs to the tetrahedral group. This is tetrahedral. So we answer this. It's tetrahedral, but this does not look like tetrahedral. So you want to draw it now. Maybe you can draw it like this. This is AS, and this is 1 hydrogen, and this is 1 hydrogen, and this is 1 hydrogen. Now the question is, what is this angle? The angle is tetrahedral angle. Okay. So in our table in the previous page, we didn't mention the angles, but you should know them by now. The linear has 180-degree angle, trigonal has 120, and tetrahedral has 109.5. So this one should be equal to 109.5. But because this electron pair needs some space, we expect this angle to be actually a little bit lower than 109.5, maybe 109, 108, 107. It depends on the atoms and depends on how big the acetylene is. Okay, so this angle is indeed not 90 degrees. It's indeed not 180 or 120. It's close to 109.5. To understand this better, so we answer this question. This is tetrahedral, and the shape is, and we'll talk about the shape. This is called trigonal pyramidal. Trigonal pyramidal is the shape or the molecular geometry. So you have two things. It belongs to tetrahedral group. So the arrangement of electron pairs is tetrahedral group, but the shape or the molecular geometry is trigonal pyramidal. Or you can memorize this as this is B3E, because you have 3 bonding pairs and 1 electron pair setting. This is just like ammonia, by the way. This one is the same as ammonia because astatine, which is this element here, AS. Sorry, this is arsenic. Arsenic is just like under nitrogen and phosphorus. They are in the same group, and therefore they make the same compounds. So arsenic, and if you go to fit.com, you can draw this, and you know. Okay. Next one is OF2. Let's do oxygen difluoride. Any guesses about its structure? OF2. Same thing. I'm gonna write Lewis first. So 6 plus 7 times 2 is equal. So for 20 electrons. Oxygen in the middle. F here. F there. How much are these? This is 8 and 8, 16. We have 2 more. So we put here two electron pairs. This is Lewis. If I ask you to draw Lewis, you draw it like that. And this is the correct Lewis structure. But in terms of VSEPR structure, what about VSEPR? VSEPR is you want to ask yourself again, what is the arrangement of electron pairs on the central atom? The central atom, you have 4. You have 4 electron pairs. You have 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs. You count the bonding and the non-bonding electron pairs as 1. So this is 4 electron pairs. And by the way, we count also the double bonds as 1. So that's what VSEPR all about. You count the bonding bonding electrons, bonding pair of electrons, and the non-bonding pair of electrons, and the double bond and the triple bond. You count them as one. So this must be tetrahedral because it's number 4. So this is tetrahedral group. But what is the shape? The shape is just like water because we did this before. This is OF2 molecule, okay, and the angle is around 109.5 degrees, and this is called the VSEPR structure, and it has bent shape, bent. Although it belongs to the tetrahedral, but the shape or the molecular geometry is called bent. So if I ask you now why this is important, because this will explain the physical and the chemical properties of the compound. So for example, if I ask you if this is polar or not, you say this is polar because this is more electronegative element that will pull the electrons this way. This also gonna pull the electrons this way. So the net pull here is to go down, and therefore this is a polar structure. You see here, I'm using the VSEPR structure to determine polarity. You cannot use Lewis to determine polarity. Actually, according to Lewis, this is non-polar, and this is wrong. And that's why Lewis itself is a failed model. A better model is the VSEPR one that expects the actual physical or chemical properties of the compound. So this molecule is polar. The next one is AlCl4 minus. Okay, let's do this as well and see how does it look like. +1. Why +1? Because the one is for the minus, which is the anion. So 7 times 4, 28, 29, 32. There is a lot of electrons here. 22 electrons in this compound, okay? Double check again. 7 times 4 is 28, and 4 is 32. So there's AlCl4, that means Al is in the middle. I'm drawing the Lewis first. So 4 Cl's, okay? Now this is Lewis, and Lewis is a first step to draw a VSEPR structure. So you want to put the electrons, of course. 32 electrons, there's only 8 here, 2, 4, 6, 8. That means we have to put the rest of the electrons. Let's satisfy octet rule at least for the Cl first. Give each guy its 8 electrons. So how much is that? 8 times 4, 32. So we are done. There are no electrons left for the aluminum. And this whole thing is minus. And this is something you must do when you do the Lewis structures. You have to put everything in brackets for an ion, because this is an ion, and you have to put a minus indicating this is an ion. Okay, now this is Lewis. Let's think now about the VSEPR structure. This is going to be a tetrahedral, by the way. So in Lewis, he is expecting an angle of 90 degrees. But this is wrong, because the arrangement of electron pairs here, or what we call the electronic geometry, is equal 4, because around aluminum there are 4 bonding pair of electrons. This is AB4 kind of a molecule, and we know this is a tetrahedral, and therefore expecting the geometry, you're gonna draw Al here, maybe Cl at the top, Cl here, and Cl there, and this whole thing is minus, and this is the VSEPR structure, and you know that the shape now is actually a tetrahedral again. So this one is this is just like methane, okay? The shape of AlCl4 minus is the same as methane, and the angle here is 109 degrees 0.5. It is not 90 degrees, okay? If you go to fit.com and you can draw this, and you will see that AlCl4 is actually tetrahedral structure. Okay,